Hey guys, I wanted to do a big intro showing what's about to happen in this video, maybe crack a few jokes, pretend this is a Tektronix 224 that's growing up or something like that, but I just didn't have it in me. So what you can see is me, first of all, in the reflection. Hi. But this is a brand spanking new Tektronix MSO4B series. This is the 44, so it's got 4 channels instead of the maximum that it can go up to, which is 6. It's 1.5 gigahertz bandwidth, 6.25 gigasamples per second. Yeah, the bee's knees basically of what I would call still a mid-range, I think, scope. And this is targeted at, not any more general debugging and stuff like that, but it can also do stuff like pre-compliance testing, validation for different protocols and stuff like that. It's got the bandwidth necessary for a lot of stuff and the horsepower behind it, to do quite a lot of math. This is not a sponsored video, by the way, by any stretch of the imagination. I got this from a friend, and that's all I'm gonna say. I have to give it back in a few weeks' time. I've seen that this series of 4B scopes, so the refresh of the 4 series, has kind of flown under the radar, and it's kind of a pity because these are really nice scopes and they're significantly faster than the 4 series, especially in how the user interface feels, the snappiness of it all, and I don't think there's that much improvement done under the hood, but certainly some processor hardware or firmware tweaks have been made to make this a lot faster. And it's considerably faster than my old MDO 3000 series. Note, these aren't mixed domain scopes anymore. They don't claim to be, though they're perfectly capable to do that to a certain extent. I'm going to show you, hopefully, what I mean by that. But it's a very capable instrument. I think it starts at about 9 grand at least, maybe more. If you want to get a fully kitted out one, it's gonna set you back a boatload of money. So not a cheap piece of test equipment, but yeah, if you need it, you need it. There's a fun thing that if I remember, I'm gonna gloss over again. Not gloss over, but I'm gonna bring up again. So there's some options that you can purchase for this thing, and a few of them say that they require some external hardware either, or that they require a specific number of channels. So for example, there's a motor power analysis package that you can get, but that requires 3 current probes and 3 voltage probes, of course, for the motor voltage and current. So that'll set you back another, I don't know, 20 grand at the most, I think. And there's a TDR function on this thing, time domain reflectometry, which won't work with just any pulsar, at least for now, I think. So I tried using it with this to no avail. And it requires another 4 grand in third-party accessories, so it's not even a thing that tech sells, but I'm going to show you. It's a Picotest TDR pulse generator. So without further ado, let's get into it. Oh, by the way, because I know some people are going to ask, yeah, that is a Spinergy spindle, and it is regarding Project Balcony Kern, and it is gonna be part of a series of sponsored video by Spinergy. And I know some of you are gonna notice this is looking a lot fresher because it is new. Out of sheer desperation when configuring Linux CNC, I started writing stuff on it, and not even acetone could take off these BICs. So if you want a permanent marker that will ruin one of these ESD mats, yeah, this is, look no further. So I am going to turn the thing on, and I'm going to let you see in real time how loud it is and how long it takes for it to boot. So it sounded like a jet engine there for a few seconds, but now it's not that bad. And believe you me, it's going to take a bit longer to actually do anything. It's running, this one isn't running an embedded Windows or a Windows of any sort. I think it's still some sort of proprietary embedded OS. The 5 and 6 series all run Windows, or you can get them as non-Windows machines as well. And I'm pretty sure there's an AMD processor of some description in here. My old 3000 series up there uses a PowerPC processor, so Power CPU. And that one for sure runs a flavor of Linux or something like that. So, as you can see, it finally decided to do something. Power on self-test passed. I don't know if you can see that very well, but we're greeted by the same user interface you first saw in my review of the MSO2 series. So those are basically 2, 3, 4, 5, and 6 have a very similar looking GUI. I personally don't like it, to be honest. Much to my dismay, they've all gone through the same route of, you know, setting buttons to select what the vertical knob is doing. There is an interesting thing, so I'm gonna use a you know, appropriately fancy mouse for this. If you turn display mode to stacked and enable all the channels, it will split all the channels into their each of them has their own little corner that they can reside in. I am not a huge fan of that either, and moreover, I'm not a huge fan of this vertical display here, because for me at least it's a bit less intuitive than, you know, just having all of the traces in a single display and having a gradical that's common to all of them. The one nice thing is, though, instead of pressing one of the keys here to select it, you can click on a trace, and now that trace becomes active to your changes. So you can change the offset and the sensitivity or whatever. What else is interesting to me, at least, is that it comes by default in this stacked display mode. In overlay display mode, you just get all of them like this, and the markings on the side are only addressed to the selected trace, which is very bothersome to me. So if you click 1, now it says 1 and the corresponding voltage readings are here. If you click 2, then it shifts, and you have really no way of, at a glance, seeing how big this signal on channel 1 would be with respect to the signal on channel 2. I don't know where that came from. It's not my favorite, but anyway, everybody's doing it now, so all the cool kids are doing it, so they might as well. I like the fact that all the buttons are pushable, and they center or switch to fine scale, like a vernier. So now it's basically, I'm changing the vertical in millivolt increments, basically. And yeah, this is a very bird's eye view of the whole thing. It gets a lot deeper when you start messing about with actual software inside. Oh, and by the way, the fact that it runs on a mouse with a mouse is very cool. Each of these channels can go to the full bandwidth. I think the sample rate gets shared if you turn on more, if you turn on more channels, the sample rate gets shared between them. And there's another thing that kind of weirded me out. So if I plug in this thing, for example, which is my fast pulsar that I made a while back, you can see that the screen is nice and responsive. It really is much better than a lot of older generation tech digital scopes. The refresh rate is really quite good. It's still not acquiring very fast. Not entirely sure what's that about, but it seems a lot more snappy, especially when you change settings. It's a lot more snappy. And now it's in the stupid fine horizontal thing, which I really don't like. Okay, so we have a lot of jitter because the trigger was put, you know, down in bottom, but it was still triggering quite adeptly on it. And I have an attenuator here so as not to blow the front end and the input on the oscilloscope. So if I double click this and I go to 50 ohms, you can see that the bandwidth can go up to 1.5 gigahertz now. And if I open this window here and I add a measurement, and which we have rise time on channel 1, you have to click add, which is quite annoying. You're gonna see that it doesn't really wanna measure it, and it's kind of spazzing out all over the place. I don't know what this is about, to be honest. I tried messing about with the thresholds and stuff like that, and I have verified. I've done a number of tests and I played around with it. This is up to the latest firmware, and I don't think this is a firmware bug anymore, or if it is, it hasn't been addressed, but it really doesn't like measuring fast rise times like this. I don't know why. I can do it with my eyes and a couple of cursors, no problem. So also the cursor buttons are pressable as well. And what I like is that there's two buttons for one for each cursor. So delta T 300 and something picoseconds. This is about 1.2 something gigahertz bandwidth, which is the limit of this, not of that, I hope. I haven't done too many tests with putting RF in and seeing where the minus 3 dB point of the thing is, but I'm gonna try and trust them on this. So yeah. Another thing that might be the case is that this is not a first order responding input, so I have no idea. So it might be actually better to measure from 20 to 80% the rise time or something like that. One more interesting, deceitful thing. I think you can just barely make it out here in the bottom. It says that the sample rate right now is 250 gigasamples per second, 4 picoseconds per point. Interleave time or interpolated time or whatever. This is not running in real time anymore. This is now acting as a sampling scope. And the record length is 1 kilopoint. No matter how hard I tried, I couldn't get the scope to stay in real-time mode at these kind of seconds per division settings. So if you look, the shortest time base that you can go to and still have the maximum rated sample rate of the scope is this 6.25 gigasamples per second at 20 nanoseconds per division. If I zoom, there's no zoom. This is still interleaved now. In what it's showing in the bottom, I think. But for faster time bases, you're limited to what the scope thinks it does best. Well, actually, not that it thinks it does best, it's what it can do. I'm assuming it's issue with limitations between memory buffer from the ADC or to the DSP or something like that, to the FPGA. I have no idea about the architecture of this thing in the front, after the front end, basically. Yeah, so word of warning, I'm not sure how it behaves for non-repetitive single shot signals when it comes to faster rise times. I don't think this is what it's meant to do. As a whole, it's not a single shot capture oscilloscope primarily, but this might be a limiting factor for some of you guys. And the fact that it kind of really fails to measure this thing when my 3104 does it no problem. It's a bit of a bummer, but anyway. And I've verified the performance is the same on all channels, so no, this hasn't had the #1 channel blown out of it or something like that. So yeah. Similarly to the the 2 series, this one also has the results table that you can apply to bus decoding and stuff like that. It can decode every bus under the sun. I think it's got a arbitrary waveform generator that's out on the back here, and I cannot show you the back side for 2 reasons. One, it shows the serial number and I don't want to get in trouble, and no, it's not stolen. Chill. And the second reason is that it's kind of lodged in here now, so if I try moving it, I don't know if I can move it without, doing some harm. So I'm gonna have to see how I do about giving it back. No, I'm joking. I can move it perfectly easy. It's not stuck in there. But Tektronix, if you're watching this, I like it. It's very big, but I like it. Okay, let me set up something else. First of all, I have a radio antenna that I'm gonna just stick in the front like this, and we'll try and see what we see on the spectrum view. But for that, I'm gonna need some lower sample rate. So if you click on this, you can get to spectrum view, and you can also have spectrograms and stuff like that. So if I hit display spectrum, it pops up with a nice spectrum analyzer looking like interface. This is very similar to how Tech showed their spectrum analyzer things. And you get another window that pops up here which says spectrum. And you can set the center frequency to anything between 0 and 750 megahertz, I think, or a bit higher, but the span is limited to 500 megahertz. I don't know. I think it goes to 1.25 gig. Yeah, and now you have 500 megahertz either side of 1.25 gig, which is up to the bandwidth of the scope. But let's look at something a bit lower. So I'm gonna go to 100 meg, and span, I want like 10 megs or 20 megs. And let's see if we find some radio stations. Whoops. Oh, this is an interesting thing. So if you're selecting this window, the horizontal section here acts upon the spectrum view. If you want to give it more samples, you have to click on this, so it can do its mathing on more samples like that. And we can see there's 101.8 something megahertz. That's the radio station that's closest to me. It's basically, if I look out the window that way, I can see it. So if I click on here and go to cursors, I can see 94.2. various radio stations, like the 92 point something. This one here is 106.2. So these are all radio stations. So the radio, the front end on this thing is pretty good. Whoops. Oh, and the vertical also targets the same thing. So if you want to go back here, you should go into this thing. And what else is interesting to see? Well, it's very, very fast for what it's doing. It's doing quite a lot of mathing in the background, and it's doing a very reasonable job. The noise floor of the instrument, let me see if I can... the noise floor is round about minus 100 something dBm on this line, which is very good. Much better than was the case for my older one. And yeah, it's doing a lot of math along, you know, at the same time, and it's putting out a nice spectrum view. Another thing that looks really nice on the scope, if I just go here, you also have spectrograms. And this I really like because it actually shows the scope is fast enough that you can actually see the modulation. So if I hit single, it's not going to trigger, but if I do a stop, you can see very nicely in the spectrogram that this is the modulation, the FM modulation for the radio stations that we're looking at. And I'm going to show you that a bit more clearly on, I'm going to plug in one of my RF spectrum signal generators and show you. But this is really, really cool. And there's a thing in the spectrogram. Where is it? Here. Spectrogram, and it shows the spectrum associated with the waveforms between the cursors. So in between the cursors we have about 750 microseconds. So this time here is 750 microseconds, which is really nice. Another thing it can do is that if you go in here and you go to spectrum view, it can actually show magnitude, frequency, and phase in a separate time domain frequency. So if we look at frequency over time, I hope it's not stacked, or oh, it's stacking it here. Okay, so this is delta frequency relative to the center. So if we go to a center frequency of one of the radio stations that we know, so it's 101.8. So I'm gonna hit enter 101.8. I hope you're seeing what I'm doing here. And if we hide channel 1, oops. I was expecting for it just to hide the channel, not to... Okay, so it's not displaying it anymore. So we're gonna look in here, and this is delta frequency, so it's 4 megahertz to negative 4 megahertz, left and right, around 101.8 megahertz. And if I zoom in, you should kind of be able to see that this is basically the audio signal that's in that the radio station. I am going to hook up the signal generator very quickly so I can actually show you this in a more controlled fashion. Just give me a second. Right, so what we got here now is a 100 megahertz 0 dBm through a kind of a lossy cable, modulated in FM at 1 kilohertz. So this is a kilohertz of FM, basically audio, modulating the 100 megahertz, and the peak deviation is 100 kilohertz either side of the 100 megahertz. So what we can see here is, so this is the time domain of the input signal. This is the time domain of the basically of the demodulated signal. This is actually the demodulated signal from the FM, and the spectrum up on top is the basically the spectrum of the input signal. Now I want to show you the spectrogram of the signal like this. And another thing that I really like is how snappy it is when you move windows around. So you can see that it's doing quite a lot. It's locked onto this peak here, and the interface is still responsive, it's not laggy, and it's doing quite a lot of stuff in the background. So you can see, first of all, in the spectrum you can see the fundamental and the whatever these are. They're not harmonics, they're some sort of images of the fundamental signal. I'm no RF guy, but it's pretty cool that you can see this. So the dynamic range of the ADC inside here is really good. It's claiming that right now it's on 12 bits, so that's not surprising. So it's capturing quite a lot of detail from this signal here. And this is the demodulated signal again, as I said. What I find weird is that if I go to trigger, and select the source, it gives me the option to trigger on the frequency versus time, which would be really cool because I could set the trigger somewhere and it would trigger on that point. It will lock the spectrum to either end, basically. So if I'm triggering close to the top, it would trigger at negative 100 or 100 kilohertz when this is 100 megahertz minus 100 kilohertz. If I was triggering near the bottom, it would be 100 megahertz plus 100 kilohertz. But it doesn't trigger. If I put it on normal, it just locks up. It says it can't trigger. It says it's ready. So it's waiting for a trigger, but there's no trigger. I'm not sure if this is a bug or if the fact that you can select the trigger source as something from this here is a bug, because I'm assuming that it would be pretty crazy difficult to get it to trigger on that. Just imagine the throughput of data that's going through here. So selecting that bit of the data to trigger on would be quite difficult. And if you put it on auto, it just gets a bit faster, but not significantly. If you put it on normal trigger, it kind of stays sort of still, but not really, because you can't really trigger off of an FM signal. But yeah, okay. I'm gonna show you another thing, but for that I'm gonna need to turn on a different signal generator, one that knows, you know, complex modulation and stuff like that, and we can take a look at that. I'll be right back. Okay, so now I fed in a 100 megahertz GFS case modulated signal at PRBS 9, and it's pretending to be the DECT standard at 1.152 megabits per second. So what you can see here is the same thing. It's the frequency over time, but in this case the frequency is either all the way up or all the way down, and this means either 1 or 0. And trust me, I've tried this. I cannot trigger on this either with that thing that I was showing you a couple of seconds ago, which is kind of annoying because that would be really cool, especially if you could trigger off of this looking for a pattern. For example, something like a 101 or something like that, that would have been really cool. But if you zoom out enough, you can actually see the PRBS sequence repeating. You can't in this window because it's too short, but trust me, you can. So I showed you that you can plot frequency deviation. You can also plot, in the spectrum view, you can also plot phase. Magnitude isn't that interesting because it's here. This would be useful for AM modulation, but I don't have anything that does AM. It's ridiculous. I have stuff that does FM and complex modulation, but not AM. I have no idea why. It can also do phase. So let me just pause it again a second. I'm going to enable the phase thing here, and hopefully we're going to be able to see some phase data. So in the same sense as what I've seen so far, but with a PSK modulated type signal. I'll be right back. Okay, so this is a QPSK signal, and you can see the phase doing all sorts of stuff in here. If you stop it, it looks almost unintelligible to me, but you can sort of see this is a 180 minus 180 minus 45 or something, 50, 60, etc. 0. So there's definitely some symbols going on here, and this thing is demodulating it and showing you the symbols. I don't know if it can do something like a constellation, but yeah, I don't know. I haven't tried enough. I didn't see anything like that showing a constellation for a QAM or something like that type of signal, but it probably can be implemented in firmware. I have no idea. It's beyond me. Interestingly though, because it can plot phase and amplitude over time, you can actually do Bode plots and frequency analysis for loop stability, for switching converters and stuff like that, and there's all sorts of stuff in here. So let me just show you the license options. So just look at how many of these are available. So you have audio, automotive, computer, which is RS-232, 422, 485, UART, etc., etc. SM bus, one wire, EtherCAT, which is quite interesting. Ethernet. You can do power analysis, advanced power analysis, and this one, which is the one I told you that it requires more or equal to 6 channels. So this is quite nice. I would like to have a go at playing around with one of these and the Spinergy spindle and see how well they drive that spindle, because you could tell a lot about the way an inverter works using this information here. And it also has stuff like stuff for testing wide bandgap semiconductors, like reverse recovery measurement for silicon carbide and gallium nitride, all sorts of stuff like that. These are the hardware options. It has something for signal integrity, which is the mask and limit testing. So you can apply masks to any signal and do pass-fail testing basically. And this is the RF, which can actually decode NFC packets. So if you're working with near field communication, that might be useful. And this is the TDR thing that I was telling you about. So let me just turn off everything for a second, and I'm going to go to File and Default Setup so we can clear everything up. Let's give this guy a break. It's doing a great job. If you go to Measure, you see all the plethora of measurements, and I think all of these come kind of standard. I'm not entirely sure, but this is the TDR thing that I was showing you. So I'm gonna hit Add. It's not gonna do anything because it cannot be bothered, but it says that the TDR source is supposed to be the Picotest J2154A. This is a $4,000 bit of kit that they're asking for, so it would be nice if you could, I don't know, put something like this or another pulsar, have it memorize what the pulse looks like, stick a thing in it, and do TDR like that. So you're not forced to buy another $4,000 of stuff. But anyway, I'm just nitpicking at this point. Okay, another default setup. Oh, almost forgot. The so bus, you can do anything. You can have all of the types of buses, so you can see just how many of them there are here. Some of them I haven't even heard about, like Manchester stuff, probably stuff that I'm anyway not supposed to be working with, so it's very complex stuff. And another thing that I really like is how nice the FFT looks like. So the FFT is very, very responsive. So let me just turn on the Stanford Research Systems and use it as a signal generator, because it's pretty good. So the reference oscillator in it is pretty good. So we have a 20 kilohertz here, and the FFT is of course all the way down to incredible 3 gigahertz, but we don't need that. So we're gonna look at something more reasonable, such as this is 1.5 megahertz. I have no idea what that is. It's been on ever since I got this apartment, so I have no idea what that noise is. Radio stations you can pretty easily see at higher frequencies. So this is all the radio frequency, the radio stations around us. So literally what I was showing you in spectrum view, you can see in a different way in this FFT, which is really, really nice. And this is terminated into BNC, so it's also looking at a lot of other stuff. Quite an impressive front end on this thing, I gotta admit. Okay, let's crank it down to till we go to about 120 kilohertz. Okay, so this is the peak. This is the 20 kilohertz that we're looking at. So if I click a cursor in here in just a second, I'm going to click a cursor off of here and put it here, and move it to this thing. You can see that if I manage to nail it, it's 20 kilohertz. It's 155 milli dBm. You can actually configure the output to show in volts RMS. So, oops, where is it? Come on. Huh, interesting. This might be a bug, so this hasn't got any effect on it anymore. Interesting. I'll just put it back to, and you can see these are all either harmonics, but we can verify that for sure in just a second when I shift the frequency the thing is spitting out, or it's other noise that it's picking up. So very, very sensitive front end. I'm gonna just change the frequency a bit so we can see what moves with it. There's a lot of averaging going on, as you can see. So this is just noise. I can't see any harmonics on the output of the generator here. So if some of these would have shifted with this, it would have meant that they're harmonics that are being generated by the signal generator in the Stanford research, and we would have seen them move and change in height depending on how they fit in the various filters or whatever. But in this case, it looks like a very clean sine. The noise floor for the FFT is a bit higher, I think, than the noise floor for the spectrum view. It's minus 70-ish dB if you don't take into account all this grass that's growing here, which is probably the fault of my lights and stuff. I don't know, but again, pretty impressive in how nicely this thing moves. Okay, now I got to show you something less impressive. So I'm just gonna delete math 1 and I'm gonna try and make it alias. And it's not gonna alias with this because it's too slow of a signal, but if I take it out from here and put it into the RF signal generator and disable the modulation, let's see it alias. So this should be 100 megahertz, with no... Oh. Yeah, look at this. It's aliasing like hell. How can an oscilloscope in 2025 alias like this? So this is 100 megahertz, and it's pretending it is, I don't know, 50 hertz. And it's not even warning you that it might be aliasing. Okay, let's try and stick it back into 50 ohms, because that's probably why we saw that the FFT was a bit noisier, because it was a poorly terminated environment. So let me crank the frequency on this to 1.5 gigahertz. 1.5 gigahertz. And I don't know how much it dropped. Did you see how much it dropped? I don't remember. Let's just... Oh, I hit accidentally 1.7. So this is 1 gigahertz. Let's add a measurement and look for that 0.707. 50 millivolts. So this is... I can't convert it into dBm off the top of my head, but let's take that as a... So this is 100 megahertz, 200 megahertz, 400 megahertz. It's dropping already. 900 megahertz, 52. It's not 0.707 yet. And this should be pretty close to 0.707, and it's 1.5 gigahertz. Yeah, and let's see if it can measure the frequency on this. 1.501. Yeah, well, it has the bandwidth it says it does. I was expecting a bit more, to be honest, but I guess in today's time you pay for every last millihertz. Older tech scopes, because the things with me and tech scopes. Older tech scopes were very conservatively rated when it came to bandwidth. So, but this is common practice in these days. Nobody's trying to impress anybody by having a 2 gigahertz bandwidth scope sold as a 1.5 gigahertz bandwidth scope. Now, if you're paying for 1.5 gigahertz, you're gonna get 1.499 or whatever. But other than that, I really like the scope. It's very nice, and especially the fact that it's so snappy and it moves really quickly. It thinks fast. It's got a lot of options. You can get to do basically almost anything within limits, but it's it's far too much scope even for me. But yeah, Tektronix, if you're still watching, thank you, and thank you for watching, but I would really like one. The 6 channels, please. I want to do the motor stuff. Yeah, I don't know. Are you waiting for some conclusions? Because I don't really have any. I couldn't have been exhaustive in my testing of this scope, because again, I have a lot of test gear. I am, I'm a member of the Both Anchors Anonymous. I have a bumper sticker and I pay my debts and stuff like that, but I don't have nearly enough test gear to validate that this thing is a good scope, or to show you exactly everything that it can do. I would need about another 100 grand of stuff to show you what it actually can do. So bang for buck, I cannot tell. Yeah, not even at work do we need such scopes. Yeah, I really like it though. You've seen that I refrained from touching the screen because grabby fingers and touch screens don't really don't really go together very well. But yeah, other than that and the few bugs that I've found, especially the thing with the triggering, this is a really, really cool scope. And again, it's significantly faster on its feet than the previous generation, the non-B model. I have some insider knowledge that the 3 series might be getting a refresh as well, so might be looking in the future for a 3B as well. And speaking of techs, I might be able to show you 1 or 2 of their crazy new probes, either the ISOView or the brand new one that they put out, which is basically it's a probe with optical isolation that you solder on a current shunt in your application, and you can see basically like having a current probe in circuit exactly there with minimal impact on the circuit's performance. That's pretty cool. It's targeted at, you know, newer stuff like gallium nitride, silicon carbide inverters, drives, power conversion and stuff like that. So keep a lookout. Maybe in the next few months we'll get the privilege of looking at one of those. Yeah, so if you've made it this far, I salute you. I really like to hear myself talk, and hopefully some of you are gonna like hearing me talk about this thing, and I hope I did it justice, because it's, you know, it's really cool. And thanks for watching, and have a great day. More tech content coming soon, as well as CNC content, because, you know, the elephant in the room is there, and I'm waiting for another elephant to arrive, and the same region is this. Just let me show you how cool these HSK 32 tool holders are. Just look at them, they're so pretty. Whoops. And the mounting mechanism on the spindle is just a work of art. Okay, I think I just made more publicity for Spinergy than for tech in this video, but you know, thank you again for watching, and I wish you all the best, and have a great day. Bye bye.